So we've all heard the headlines, right? Quantum computers are coming, and they're supposedly gonna break all our encryption, spilling all our secrets. But there's another side to this coin, a part of our digital security that's just as critical and just as vulnerable. I'm talking about authentication. And that really is the question for today. Can a quantum computer do more than just read our messages? Could it actually impersonate us? Forge our digital signatures? Could it completely shatter the very idea of trust that our entire digital world is built on? Well, spoiler alert, the answer is a big, resounding yes, and we need to understand why. To really get why this is such a big deal, we've got to pop the hood and look at how the digital signatures we use right now actually work. I mean, this is the magic behind everything from secure software updates to online banking. It's how the internet knows you are who you say you are. So, our two heavy hitters, the ones you see everywhere, are RSA and ECDSA. They're both built on some really clever math. They rely on problems that are just ridiculously hard for our normal classical computers to solve. For RSA, it's about trying to find the prime factors of a massive number. For ECDSA, it's a related puzzle called the discrete logarithm problem. For decades, the sheer difficulty of these problems has been our fortress. But here's the thing, here's the catch. It turns out that those very specific mathematical problems, well, they're exactly what quantum computers are born to do. Using something called Shor's algorithm, a quantum computer doesn't see these as hard problems at all. It sees them as puzzles it can solve, and solve pretty darn quickly. And just like that, the entire foundation of our digital trust crumbles. And this, right here, is the heart of the matter. This threat isn't just about keeping things secret. That's confidentiality. It's about being able to prove who you are. That's authenticity. Think about it. It's one thing if someone reads your mail. It's another thing entirely if they can sign your name on a legal document. Both are now on the table. Okay, so if our old methods are basically on a countdown to extinction, what's the game plan? Well, the good news is the world's smartest cryptographers saw this coming from miles away. And they've been building the answer, a whole new generation of cryptography for this new quantum reality. And they're called post-quantum signatures. The name kind of says it all, right? These are digital signature schemes built from the ground up to be tough. They're designed to stand strong against attacks from your laptop and from a giant futuristic quantum computer. We're not just patching the old system, we're laying a brand new foundation. So how do they pull this off? Well, the basic idea is pretty straightforward. We just switch to a completely different set of math problems. We find new problems that we're confident are hard for everybody, classical computers and quantum computers alike. The goal here isn't a quick fix. It's about creating a new gold standard for authenticity that's going to last for generations. So let's take a quick spin through the neighborhood and meet the new kids on the block. We're not going to get bogged down in the super complex math, don't worry, but it's good to know the main families of signatures that are really leading the charge into this post-quantum world. Now, there are a few different ideas out there, but three main approaches have really jumped out as the frontrunners. You've got lattice-based, hash-based, and code-based cryptography. Each one is built on a totally different kind of hard problem, and as you might guess, each one has its own set of pros and cons. Lattice-based cryptography is a huge favorite right now. In fact, if you've heard about the new standard for post-quantum encryption, called Kyber, well, this is its cousin. It's all based on the geometry of high-dimensional grids, or lattices. Turns out, finding your way around one of those is an incredibly tough problem to solve. Then you have hash-based signatures, which are really interesting. Their security comes from something we already know and trust really, really well. Hash functions. They're like the digital fingerprints of data. The security proofs are rock solid. The only trade-off? The signatures themselves can be, well, a bit chunky. They take up more space. Okay, so this all sounds fantastic. We've got a problem on the horizon, and we've got some brilliant solutions ready to go, which, of course, probably has you asking a very logical question. Yeah, if these new post-quantum signatures are so vital and so secure, why isn't my phone using them right now? Why hasn't my web browser already made the switch? And that's a perfectly fair question. The answer comes down to a few very real, very practical challenges. It really boils down to three big things. First, these new keys and signatures are just bigger. They take up more data. Second, they're newer. They haven't had decades of real-world testing like the old ones. And third, and this is the big one, you can't just flip a switch. It requires a massive, coordinated upgrade across the entire global internet. Every server, every piece of software, every device. And this table here, it really lays out those trade-offs in black and white. Just look at the key and signature sizes. We're going from smaller to larger, and in some cases, significantly larger. That can be a real issue for small, low-power devices. And performance can be all over the map depending on which scheme you choose. So it's a constant balancing act. And that's just the tech side. On top of that, you have the human element. Getting all the big tech companies, governments, and engineers from all around the world to agree on a single set of standards, that is a massive, complicated process. It's happening, led by organizations like NIST here in the US, but it just takes time. And hey, just to be super clear, our goal today was to give you the big picture. We're not diving deep into the weeds of the math or comparing specific algorithm parameters, and we're definitely not looking at any code. This has all been about understanding the why this is happening and the what we're doing about it. So as we wrap things up, let's just nail down the key takeaways. Number 1, the quantum threat is real and it's coming for our authentication, not just our secrets. Number 2, post-quantum signatures are the solution, and they're designed to be future-proof. And number 3, they work because they're built on completely new and different kinds of math. You know, in the end, making this switch to post-quantum signatures, it's so much more than just a simple tech upgrade. It's a fundamental step we have to take to make sure our digital world stays a place where we can actually trust each other, verify information, and operate safely for decades to come. It's really about building a new foundation of trust for the quantum age.